Uh, s- so Today we're gonna look at the reinforcement learning, Q-learning, for the SI2215 AI project. So we're gonna dive right into it. So just uh, just a notice: this presentation will be quite short, but the details are far much written inside the report. So this is just an overview of what this project was all about. So we're going to look at the reinforcement learning, Q-learning, taxi problem, cat pole problem, and mountain car problem just at a glance. So reinforcement learning, I'll literally take us back to machine learning. We saw that we had machine learning divided into three: uh, supervised learning, unsupervised learning, and reinforcement learning. So reinforcement learning is concerned with intelligence and how intelligent an agent ought to take a specific actions in an environment in order to maximize the notion of cumulative reward. In simple terms, we can say we are training the machine learning agents to make a series of decisions and actions so as to maximize the incentive. So we can look at the picture here. An agent here is the dog, the environment, and then we have the actions the dog is supposed to perform, and he can get a reward. The reward can either be positive or negative. So in this scenario, the human throws the stick, and the dog is supposed to fetch. So the action is fetching the stick. So if the dog picks the stick, the human will say, good boy, or gives the dog a treat. So that's a positive reward. Um, and if the dog does not perform the specific action, the reward will be negative. It will be like stop or bad boy. So that's a brief look at this reinforcement learning, and we're going to move directly to Q-learning. So Q-learning, we can see we have a small diagram there. Also, it's a bit of self-explanatory if you've looked at what we said about reinforcement learning. And so for Q-learning, it's a model-free reinforcement learning algorithm that is used to learn the value of an action in a particular state. So this is a bit more explanatory in terms of the title itself. Q stands for the quality. So we're literally looking at the quality of the action. So it's value-based learning algorithm, and it updates the value of the value function based on an equation, looking at the Bellman equation. So it poses an idea of assessing the quality of an action that is taken to move to a state. So how does it really work? So with all terms constant, that is the action, the state, the environment, and the agent, we still have the Q table and the Q value. So in Q learning, we work with the Q table and Q values. The Q table is initialized at first to 0, and um, at each state we explore the possible actions and choose one. So up when we move to the when we perform the action, we move to the next state, which was as a result of the action taken. So for all possible actions from the state, we select the one with the highest Q value and update the Q table using the equation. So we set the next state as the current state as we move forth and forth. So if the goal state is reached, then that's the end, and we repeat the process. So the Bellman's equation, it's clear enough from as you can see. So the Q values are initialized to an arbitrary value, and as the agent exposes itself to the environment and receives different rewards by executing different actions, the Q values are updated using this equation. So we have the alpha, which is the learning rate, and it is the extent to which our Q values are being updated in every iteration. And then we have the gamma here, the gamma, which is the discount rate or the discount factor, and it determines how much importance we want to give to the future rewards. So we can see the equation in full here. It's well explained, and we'll look at it more. So we have the taxi problem. So what literally we have to do here is we have this taxi here, and this taxi is, let's say for example, this is the taxi environment, and the taxi is supposed to pick a passenger from a specific coordinate or a specific spot and move and drop off the passenger at a different spot. So we can have we have, for example, in this image which I got from the internet, we can see that the person is here and the drop off location is here, and we can see the these lines, these block lines are walls. So literally we'll use the Q-learning algorithm to try and uh, uh, maximize the rewards for this taxi, which could be a point for a successful pickup and a successful drop off of the passenger from this point Y to this point R. We say it's red, green, blue, and yellow. So from point yellow to point R, red, we have to pick the passenger and drop them off. So we'll the explanation of how the Q algorithm works and the code is explained more in the report. So we have the cart pole problem, and in this problem the goal is to keep a pole connected with one joint to a moving cart. So the problem presents a defined set of states which include description such as angle of the pole, the position of the pole, the velocity of the cart, and the velocity of the pole. So a little shift in the angle is the primary requirement to keep the pole balanced on the cart. As a result, there are two actions representing the action space. It will either move right or move left, as you can see. So a reward is provided for every time step that the pole remains upright. The episode ends when the pole is more than 15 degrees from vertical or the cart moves more than 2.4 units from the center. More about this is explained in the report. So finally, we had to pick one extra problem and try and explain it and write a report on it. I chose the mountain car problem since it seemed a bit like a good game. So simply the mountain car problem, the car is a one-dimensional car. It's like a game, and in this case the car doesn't have oil, so we cannot be able to just drive it up to the hill. So what we need to do is we need to use the power of the car to swing it back and forth, increase the velocity so it can be able to target. So the action space in this including pushing the car left and pushing it right, and no push at all. So there are times where you don't need to push the car. Let's say, for example, if the car is at the starting of this line, for example, we probably wouldn't need to push it, and it will probably just accelerate off and finish at the end. So that's my presentation, and more detail about the algorithm and the Q-learning is written on my report. Thank you.